Okay, today we will finish the classical mechanics part, and let me just recap. We are now in the three-dimensional area where we have a force which we have called K over R squared in the direction of R. But we could also have another force which is also central, a central force. This is a central force, it just depends on R. We could have another one which is the harmonic oscillator. The harmonic oscillator force is some other K times R or times the vector R. K times R times the unit vector R. So this leads then to a potential. V is equal to a half K R squared, and that is equal to a half K x squared plus y squared plus z squared. So the harmonic oscillator is just a sum of a harmonic oscillator in the x direction, a harmonic oscillator in the y direction, and the harmonic oscillator in the z direction. And so this is also a very simple system to treat, and it's treated very often in physics. But we will look at this one, which leads to a potential V of R is equal to K, this K over R. And remember, this K is a negative quantity. We have defined it as being for the for the movement of planets. What is it? What's this value? G, M, and M. No? So that is the force. By the way, it is the same as the force between an electron and a proton. It has the same force, being 1 over R squared force, and the only thing that changes is this constant. But the K, the form of the constant is the same. It's a 1 over R for the potential and 1 over R squared for the force. So we know how to do this, then we know how to calculate electron around a proton, and so on. That we can then do as well. So it's a more general result which we are arriving at here. So what did we do? We said, well, let's look at p squared over 2m plus v of r for this force, or for that matter, and then we could write this as pr squared over 2m. Now, do you know what pr? Somebody asked me, what is pr? Now you see, you can write a vector p, you can write as xpx plus ypy plus z pz, Or you can write it as r PR plus theta P theta plus phi P phi. Okay? So if I write PR, I mean that. That's what this thing is. And there's nothing of these two parts in there. Those two parts, which I should actually write now, P theta squared over 2m, P phi squared over 2m, I write in a different way. I write this as L squared over 2mr. And then we have to add the potential V of R. And then we know that L squared is what? It's angular momentum. What property does it have? It's conserved. So once we've set up a thing that starts going that way, we define L squared, and then that is fixed. And then we are left with a one-dimensional problem. Only a problem in the direction of R. So this, of course, is our energy. E is equal to. E is that and that. So we squared there. So we call this thing here V effective of R. And that we can draw. For instance, for the harmonic oscillator, the potential looks like this. It starts here at R is equal to 0, and then it goes up like R squared. And then this thing comes down like this. And the total thing I get is, sorry, I start off there on the line, and then I go this way. And it looks like this. So this is V effective. It looks like that. And similarly for the case which we really want to do now, the 1 over R force potential goes like that. This other thing goes like that, and if we put them together, then we get something that could that goes like that. So we have something which is negative here. Now, if L is very large, it will not be negative. Then if this is a specific value of L I chose, if I chose L is equal to 0, then I'd just be on this line, on the potential line. There would be nothing from the other side. If L is very small, then I'll go almost like this and then go here. And if L is very large, for very large L, what would happen? Someone must know. Just think of it. If I don't know, then nobody knows. So what happens if L is very large? What happens then? L is very large, and this thing goes like this. And then the effective one goes like this. Okay? So it doesn't go below 0. And what does that mean? What does it mean if what does it mean if this thing is below 0? What does it mean? Circular. Okay. But what does it mean if the potential is lower than 0? It means that possibility of what?
Possibility
Of
compound to
that it is bound. You see, if we had this discussion the other day when when we are far away at infinity, and we come and so on, closer here, then this goes down, which means we can actually take some energy away and this thing can still exist. And so it will be here in this area and it will be bound. And once it is bound, it can't go away. Okay? So like our Earth is bound to the sun. And it is because its angular momentum is such that it is such that it is negative here, that the potential, the V effective is negative there, and so it is bound. Do you understand this? So what happens if I have this then? If the angular momentum is very high, then this is the V effective, is this one. This one. This is the term from L squared over 2mr squared. And this is the V effective. And so what then? Someone come up with a proposal. What are the possibilities? Then choose one. We said here it was bound, and there, of course, it's not bound. It's free. So that means if this thing has too much angular momentum, the force is not enough to hold it, and so it flies away. And so it is not in a orbit around, say, the sun. It may come along here and come to a certain point, and then it turns around, like here's the sun. This thing comes around with a high angular momentum, and it turns around and it flies off again. It is not bound. Okay? So this is a condition for binding, is that this is negative. The sum of these two must be negative. It's Monday morning. You are not quite awake yet. Someone ask a question? Okay, so let's continue. So we're looking at this force of the gravitational force, and as we said, we're looking at a case where L is such that the total force goes negative, and then it goes something like this. So a particle comes in, and it can be here and it can be bound. This is what I'm interested in. It is the motion of the sun, of the Earth around the sun. It's the motion of the moon around the Earth. It's the motion of any satellite around the Earth. It's all in this. Now let's try to find this point here. At that point, if we place a particle there, or the sun, or a planet there, then it is bound. It cannot move in forwards and backwards because it's at the minimum. So it is what? Stable. Yeah, stable in what respect? It's still moving in a circular orbit. So it is a totally circular movement. It is not an elliptic movement. It's totally circular. It's always this distance. Here I plot R. Right? It's always this distance away from the sun, say. So it's a fixed distance, and the movement is circular. What is the angular momentum here? L is equal to? So if I have a circular movement, then there's a speed there, which is the speed here, the momentum or the speed is r times omega, or r times theta dot, as we called it. No? And now I look at the angular momentum. Angular momentum is equal to r cross p, and so this is another r, and p is m r omega. Okay, or m r theta dot. This is the circular movement which is taken. So this is that situation. So let's find that point. How do we do that? Must do? We must find the derivative of this thing. So we have V effective is equal to L squared over 2mr squared plus V of R is K over R. Huh? This is the case we're considering now. And so this is a function of R, and so we find the effective dr, and that gives me, this you can do quickly. Help me. L squared over mr cubed, huh? Minus k over r squared. And so I can and this must be equal to 0. And so from this I get a condition which says R0. So this is at the point R0 where this is 0. At R is equal to R0, that will be 0. So I can put 0, 0 there. And then I can solve, I can put that guy up there and that one there. And I get minus L squared over mk. So k is a constant, m is a constant, L squared is the angular momentum which I chose to start off with. And then I can get, then I know what is the R0 that fits to that. And then I can put that into this equation. And if you do that, I can find this value, this value here of the potential. And so what I want to say is, what is V effective of R0? And I don't want to do this now in detail because I think this is something you guys don't have a problem with. So what I do is I just put R0, this value I put in there, and then I simplify a little bit, and then I get this. So I have a fairly good idea how that curve looks. So let me start again. I choose an L, and all the other stuff is determined once I've chosen L. And then that gives me that result. Now the interesting point is, what happens if my energy is a little higher than this specific energy? So my energy is not here, not this value, which I have calculated here. That is the energy which the system has for circular motion. It's this value. We've just calculated it. Okay? Should I do this or? We've just substituted R naught in.
So we have two parts. The V effective, we have two parts.
Two parts.
Yeah.
Yes.
Pressure.
And I've substituted it, and then I simplified it. Okay? So I've left out a step or two. Simplifying. Yeah? So I took R0 and I put it in there, and I put it in there, and I simplified the equation, and I get this result. Okay? I think you can just try that yourself. It's really simple. Now we already know what the angular, how long it takes for this thing to move around. It moves around with the angular speed of omega. So this omega, with which it runs around in the circular case, is L over m squared r, and if I am at that point, then this is r0, and this is squared. So this is the frequency with which it goes around. Huh? Now, there's this next point is, I decide to give the thing more energy without giving it more angular momentum. The angular momentum stays the same. So I stay on this curve, because that curve is fixed once I have fixed the angular momentum. But I give the system more energy. So it gets more energy and it sits there, it goes there. Huh? That is the energy it has. And now you can see what happens. It can be here or it can be there. And in general, it will just move around here like this, as we have seen before. Because this, very roughly speaking, is a harmonic oscillator. In the simplest form, I would just make this a harmonic oscillator. So I have this particle which is moving around, but in the meantime it is also oscillating like a harmonic oscillator in the r direction. This is the r direction. So in the r direction it comes closer to the sun and it goes further away to the sun. It comes closer to the sun and moves further away again. Now I want to calculate that frequency. Now how do I do that? We have a formula for calculating the frequency of the harmonic oscillator, which is, what's the frequency of the harmonic oscillator? It was omega 0, we called it. Square root of k over m. Okay, we know what m is. It's the mass of the Earth or whatever is moving. And what is k? K is the spring constant. Right, and how do I get the spring constant for this thing? I take this expression, actually this expression here, well, let me say, I take this expression and take the second derivative. If you have an harmonic oscillator, you take the second derivative, you get k. If you have v is a half k times x squared, you take the first derivative, dv dx is equal to kx, and d2v dx squared is equal to k. Okay? So we take the second derivative and we approximate this structure by a parabolic function. So we approximate it by a harmonic oscillator. So all we need to do is get the second derivative of this at r is equal to 0, and then we have the spring constant. And okay, we've taken once the derivative already, and so we derive this again. So d2v effective dr squared is equal to, come on now, you must help me again. This is now plus 3l squared over mr to the fourth, and then plus 2k over r to the third. Okay. It's the 2 comes from this. Oh, this 2 must go, huh? Yeah. Okay. So we can now use the result that we know what is the relation. We can use what is R0. We can put that in here. So we want to calculate this at R is equal to 0. So we 3L squared over M, and now R0 to the fourth gives me L to the fourth here, down there. And then M to the fourth, L to the eighth. M fourth, K to the fourth. I hope this comes out right. And that is minus, this is plus. There's a minus here, and no, it's minus, huh? I don't think I'm doing this the simplest way. I mean, this result, is right. I think it's simpler to just insert in this result, we insert L squared is equal to minus mkr0. We take that result and we insert it in there. So that's this result. We insert it in there. And what did I do here? Yeah, I want to take this out. we're taking this result now and we're putting this in here. So for L squared, I put in minus mk r0, and underneath I have m r0 to the fourth. And there I have, no, R0 to the third, because there's an R0 coming up there, and so it's R0 to the third. And I put in here 3 R2k over R0 to the third. Okay? Is that right? Somebody checking? What is it? 2k here, yeah, okay, 2k over R0 to the third. And that I can cancel. And sorry? Here, to the power 4. Okay? And now you see this, now I cancel that with that, then it becomes to the power 3, and there's that term is there. And so in general, I just get k over R0 to the third. So this is what the spring constant is. Everybody happy? Is it correct? Okay, so this is the spring constant. Now we want to calculate the frequency with which this thing moves in the r direction. And that is equal to this spring constant, which we have just calculated, divided by k effective over m, and that is equal to minus k over mr0 to the third. Square root of that. And now for the k, I'm again putting in the k, I'm putting in L squared over mr0 with a minus. This is a function which we have. And so I get here, that is equal to L squared over m squared R0 to the fourth. Just do this yourself. Just put that in there. There's a minus there, there's that, and so on. And there's an m to the third, there's a r coming in there. There's a r to the third, and there's a r0 coming in there. And so we get this expression, of which we can take the square root very easily. So this is L over m R0 squared. Okay?
Do you take a single?
Plus or minus? No, we just take the plus sign. No? I don't know. The minus might mean turning around the other way or something, but it's just L. Okay, so remember we've chosen an L, we've calculated an R0, and now we have a frequency with which this thing moves around this circular movement. But if you look at this expression, it's the same as this expression. And so what does that mean? So this was an omega, which was what? Circular motion. And this was another omega, which was going in and out. So these two frequencies are the same. And there's actually no a priori reason why this should be so.
Because the CPR movement is for some magnitude a certain.
Say that again, speak up loudly, fortement.
The CPR movement is the sum of two oscillator movements.
But I mean, did you expect this to happen? That this frequency going around and this frequency of moving in and out is the same? You didn't? No, I didn't either. So there is another symmetry in the problem. The problem actually tells us there is a symmetry here which we haven't really taken care of. I mean, we know about the angular symmetry, the rotational symmetry, but here there's another symmetry. It says that the one motion is linked to the other motion, giving the same result. And this, for any theoretical physicist, means you have to go and do some work and check why is that so. I mean, this is not just a chance. It doesn't happen just by chance that this happens. There must be a basic reason for it. And as I indicated the other day already, this actually means that if we have a motion like this, an elliptical motion, once it's set up, it will always stay like this. It will not turn into an ellipse that goes like this. It changes. It'll always, this ellipse, once it is set up, it will always stay in this position. So I could say here is a vector showing in that direction, which is conserved, which will not change. And the interesting point is that this is only true for the potential 1 over r, and for the harmonic oscillator you have something similar. It's only true for the potential 1 over r. If you change that potential, the 1 over r potential, to something else, which is still just a function of r, but it's not 1 over r, it's something more complicated, then that will not be true. And if you have a little program in which you can do generate the motion of planets, you can in fact try that out. You can change that value of the potential away from 1 over r in some simple way. Say make it 1 over r 1.1 or something. So you change the potential from 1 over r, you change it to 1 over r 1.1, something like that. Then that will not be true. And this is sort of, there is another symmetry in this work which is only valid if the potential is 1 over r. And what is interesting is that this symmetry you will also find in a different way, you will also find in quantum mechanics. You will also find that this symmetry exists, and it exposes itself in a different way in quantum mechanics. So what is a symmetry? It goes under the name of some very important people who actually found that, and that is Laplace, Runge, and Lenz. And this morning I quickly Googled the Lenz vector, and I found this also under these names. And there's a very nice article on Google which contains, in Wikipedia, which contains all this stuff, plus a lot more of what I can possibly tell you. And so the vector they found was called a vector A, which is constructed by P cross L minus MKR. So this is a vector which lies in the plane. P L is out of the plane. We have the motion. L goes, the movement goes like this. That means the vector L goes out of the plane. P is in the plane, and then P cross L is also in the plane. So it's a vector in the plane, and it's actually the vector which I showed just now, and which you can now easily prove for yourself that this is a conserved quantity for the for the specific potential which it's conserved for the potential but only for that potential. For that potential, it is a conserved quantity, and let me do that quickly. If we take dp So what is this? Yeah, but what is the value of this? 0. And this is F cross L. And so this is, minus mk. And F cross L, L is outside, well, we just put in the size of F minus k over r squared, or capital K, or plus. I put there minus yeah, I put that in this K is now a positive quantity, not like we had a negative. So let me use this. So these two quantities are perpendicular, and they are in the plane, and so they are. If you calculate that, so it's this must be r squared. Sorry, it's a force, k over r squared. It is in the plane, and in the plane is the theta direction, and that thing is also r dot is also, I wrote the transformation, and r dot was theta dot in the theta direction, so that is mk theta dot in the theta direction. And somehow I made a mistake with the angle. With the sign. I'll try to fix it, but these two signs cancel. This cancels with that. And maybe this is minus theta. I don't want to waste your time, but I can assure you, if you check these things, these two show in the opposite direction and they cancel, and so this is 0. The first term is plus. Okay, you can show that.
Because as cross I is the opposite of theta direction.
Okay. Okay. Oh, theta dot, yeah. Yeah, theta dot, of course, yeah. That is the length, it's just the directions of these two. But they happen to be, I'm glad that somebody is checking it so quickly. But you can check it yourself. The steps I took here are basically simple. And so that is then 0, and that is the result of the Laplace Runge-Lenz vector, which is conserved. And this, as I said, this vector lies in the I don't want to discuss this now, but this is very nicely discussed in the wiki Wikipedia description of the Runge. You can see it there very nicely there. And it actually shows this vector lies in this movement, lies like this, and it's conserved, and so this thing cannot change. While if you change the force here, of course, then this will not be true, because then this one wouldn't cancel that. If you put in another force here, it will not cancel this out, and the vector A will not be conserved. Okay? Any questions about this? So what we found is there's another conserved vector here, and that conserved vector will transform into a similar vector in other parts of physics, and where we consider this term. Any questions now? How do I get it? It's there and it's there. How did I get this? I used this result. R squared m theta dot. And I know it's showing out of the board if I draw my movement in the board. So, and that L is something I picked. I remember which I picked an L that gave me a movement in a plane. And so we know a couple of things now. First of all, once you've picked L, the movement in the plane is fixed. It's a fixed plane. You can't turn it around because L is showing in a very specific direction. And now we see that also if you get an oscillation around the circular movement, then that thing is also in a fixed direction. So it's a very fixed sort of thing. I think one of the things we could possibly do is just think about. I'm finished now with classical mechanics, and one of the things we could do is, for instance, calculate a little bit about the energies. How big are these energies? Do you have a feeling how much the energy is of say the moon moving around the Earth? You see, we had this energy where I have a kilogram of butter and I drop it, and that was 10 joules. Huh? And then we said, well, what is it? What is the butter if I make it into oil and I burn it in some way, either in my body or with a candle or something? And we said that was a lot more. How much? 37 megajoules. So it's a lot more. And so if you then take this butter and you get some anti-butter and you put them together, then that was how much? To the 10 to the power 16. Now what do you think is the energy of the moon moving around the Earth. That movement, mechanical movement. How much is it? Is it bigger than that of we're talking about? And if so, how much about? I think you can do those little calculations. I just looked at it, and what you can do is you can take the energy of the you can just calculate the kinetic energy of the moon, which apparently, according to Wikipedia, is something like 1 kilometer. The movement of the moon is 1 kilometer per second. So it's fairly fast, huh? Yeah, 1 kilometer per second. Its mass is very big. What's the mass of the moon? The mass of the moon is 10 to the power 22 kilograms. 7 times 10 to the power 22 kilograms. And if you just calculate, well, we should actually calculate this point here. We can calculate different points, but if you just calculate the kinetic energy of its speed with which it moves, then you get something like 10 to the power 28 joules. So we should actually compare that. So that's easy to calculate. So all I did there is I took this, and I get 10 to the power 28 joules. And the question is, how much energy do we use in the world? So how do we measure energy when we talk about the consumption of energy? Kilowatt hour. So what is a kilowatt hour? Say that loud so everybody can hear.
1 kilowatt hour is 1,000 watts times 1 hour. So that's 1,000. I have to convert to joules second, to watts times seconds. So that's 600,000 seconds times 1,000.
So kilowatt hour is the way we measure things. What is a kilowatt hour? What is a kilowatt? What does it measure? Power. And a kilowatt hour? Energy. Okay, everybody happy with that? And we normally measure, if we buy electricity from the city, we pay per kilowatt hour. 1 kilowatt hour is normally a unit of electricity, which we pay. How much does it cost? About in any country, in any currency, 1 kilowatt hour, what does it cost? Madagascar is extremely expensive. I found out. I've got all the figures here, and Madagascar is very expensive, more expensive than most other African countries in electricity. Well, say about a rand or 10 American cents or something like that. That's the price for a kilowatt hour. Now, a kilowatt hour is how many joules? Would you want to write it down? Okay. Everybody understands it's right. He's right. Huh? Anybody understands this? This is the units we're using. And the units for the production in the world is not in kilowatt hours, but in terawatt hours. So that is 10 to the power. How does it go? Kilo, mega, giga. Yeah, okay. So if you calculate our consumption in the world, we have a consumption of about 5 times 10 to the everybody in the world in electricity. 5 times 10 to the power 20 joules per year. So it's still not very much relative to the energy that is in the moon. Now, do you think we get some energy from the moon sometimes? Yes. So we are actually tapping some of the energy from the moon, and but it is tiny compared to what energy there is in the motion of the moon. I think we can break now. Will you break now? And after the break, I will stop with classical mechanics now. And I will start doing some quantum physics. Okay. And just after the break, I want you all, maybe in groups as you sit, to just discuss very briefly what do you understand about under the word quantum physics. What, if I say quantum physics, what springs to mind? And I want each group of 4 or so to write down on the board 2 things about the word quantum physics. What comes to your mind? Anything. And not just the physicists. The physicists in the group can write down the more difficult concept, but I want also the simple concepts. I want all the concepts. And we write them on the board, and we see how much you understand of it. Just think about what is quantum physics. In 5 minutes we are together again. Groups of 4, come and write 2 points. 2 points about anything you think about why quantum physics, or what is it, or how is it different. Here's this idea that quantum physics has to do with the microscopic world. It is only applies to very small things. Is that right? You all agree with that? That is a correct way of thinking about it? In the big world, there's no quantum physics. It's just in the small world. Is that the way you see it? Everybody? Agreed with that? Who doesn't agree? Why not?
For the Newtonian mechanics, is just special case of quantum physics. When we apply quantum physics on the large scales, then it goes to Newtonian mechanics.
Okay, so what Ibrahim says is actually quantum mechanics applies to everything, but if I look at big things, I can always I can change it into classical mechanics. Always? No, not speeds. I'm just small and big. Is quantum mechanics just for small things or also for big things? Just for small things? Who disagrees with that? Apart from myself. Can you think about systems which are big and which you can only describe in quantum mechanics? Okay, black body radiation. The sun is a black body, sends us black body radiation. You can only describe the spectrum of the sun as black body radiation by quantum physics.
This is also can be considered to be microscopic, because we're dealing with photons, and I don't know, maybe I can, if I say I will deal with the sun and the motion of the planets, and I can explain this in quantum mechanics, that's what we mean by macroscopic world. But black body radiation also, which radiation that comes from the sun can be considered to be microscopic structure.
Okay, I'll give you another example from the stars. Have you heard about white dwarfs? Do you know why white dwarfs are white dwarfs? Because of quantum mechanics. Okay, maybe we get there. I won't promise. But without quantum mechanics, you would not understand what a white dwarf is. Okay, and have you heard about superconductivity? Superconductivity is a quantum thing. Okay, you want to say something?
How do you define small particle in physics?
Well, I didn't. Somebody defined it here. Probably 10 to the size of an atom. How big is an atom?
So the atom is said to be this a small particle.
Yeah.
Can it be the unit? Can it be the unit of small particle?
The unit of small particle. No, but there are things that are smaller than atoms. Like what?
Because I have a question about if I can take, for example, this paper. I was asking myself if you can find the number of small particles in this paper.
What do you think? How many?
Just finite.
No, infinite. No. How many do you think? The order of magnitude, I don't know either, but how many do you think, more or less?
I think that the number of particles of this paper cannot be counted.
Not countable. Oh no, that's not true. I can get a big microscope and I get 1 million students who each count one line of it. And they must count every in a microscope you can see that atoms in there. So you can count it.
You just count the number of atoms.
Yes. Yeah, you can do that. We know how many there are, more or less. I don't know, but you can check it up. They would be of the order of a big number, which is called Avogadro's number. That's a big number. And maybe it's 1,000 times Avogadro's number, but that doesn't matter because Avogadro's number is already so big. Yeah? Okay? So I just want to say this statement, and I don't blame you to write this down, because you will find it even in textbooks that people would say quantum mechanics is only applicable to small things. But it's actually the property of big things, like your cell phone or mobile phone, or many such things. They work on the principle of quantum mechanics. There's something in quantum mechanics why they work. Let me just go a little further here. At the atomic scale. Yeah, it's maybe true, but we've discussed that. The key insights of quantum mechanics, light can be a particle. Okay, particles can behave like waves, but waves gain or lose energy in quantized. I don't quite understand that statement. Oh, discrete, that it's discrete, yeah. Okay, particles like electron are indistinguishable. That's a very interesting property. That is something you do not have in classical physics. In classical physics, we are all distinguishable. We are classical bodies. We move around. You know this is Fritz, and we know that's André, and so on. We're distinguishable. And if we use even material things, we take stones or something, and you look at a stone, you can always make a little mark on it and say, that's the red stone, this is the green stone, and this is this, and so we can distinguish them. In quantum mechanics, once you get to that scale of electrons and protons and so on, you cannot distinguish them. They're all the same. And that in itself may not sound so very interesting, but they have another property which we will have to discuss, and that is that they are in two classes of things. The one class is such that if you bring a number of them together, they will always be in a symmetric form. You can exchange them, and you wouldn't really exchange something. And the other class is so that they are in an antisymmetric form. It's a bit too far, I think, but that is, and we call the one class bosons and the other class fermions, and they behave quite differently. These two, but maybe I'm going too far with that. But this was here discussed, statistical theory of nature, not statistical mechanics. Who wrote this? You. That's a very important statement. It's a very important statement. And we'll have to come back to that. That quantum mechanics is a statistical theory, but it's not a statistical theory like statistical mechanics, which has to do with thermodynamics and things like that. It's different. And we'll come to that. So that is a very good statement. An attempt to study the fundamental behaviors of nature. Everything is an attempt to do that. And incomprehensible. You wrote that. Well, maybe at this stage, but let's make it comprehensible. Quantities of energy, it depends on Pauli's exclusion principle. This is something I talked about just now, about these particles which are identical but behave in a certain way. And this is Heisenberg's uncertainty relation, and this too. Huh? So you know what Heisenberg's uncertainty relation is? Anyway, we'll get to that. Quantum physics description of a particle describe the motion of a particle. Yeah, well, classical mechanics too. We have the Broglie relation. Yeah, that's important. Planck's constant, momentum and frequency. Okay, up here, energy is not continuous, but comes in discrete, so that's important. It's not always true, of course, but sometimes. Elementary particles behave both like particles and like waves. The movement of these particles is random. It's physically impossible to know both the position and the momentum of a particle. The whole group understands this, that I've put this up? It's good. Quantum physics explain the motion of small things, among other things, yeah. Probabilité de présence. I said he must write it in French. He asked me what it is in English, and I didn't understand, but I also don't understand exactly.
I talked about for example, one electron is here in this moment, and after 1 minute, we can explain exactly where is the electron.
Yeah. So the classical mechanics, it's a good point. The classical mechanics has this idea that if you, it's deterministic, yeah. If I give you the position of something, and I give you the momentum of it, then forever, and I know the forces, of course, but then forever I know where this particle will be. I can just follow it. I just solve the differential equations, and I always know. And that is a deterministic idea. And quantum mechanics tells us that's nonsense. You can't do that. You cannot. The only thing you can do is you can predict the probability that it will be somewhere, but you cannot with certainty say it will be there. That's what you mean there. Okay. Quantum mechanics is the study of particles and microscopic level, normally a Schrödinger equation, the dependence of Schrödinger equation. independent Schrödinger equation. Okay, we will do this. Everybody knows the Schrödinger equation? We will discuss it. Huh? Okay? These people, of course, know where they were about the Schrödinger equation because they write it down and it is correct. Huh? So they know about it. Huh? Who are these people here? Hands up, please. You group. Your group. Okay. They know what it is. Quantum states are represented by state functions and okay. Quantized energy, radioactive decay is a quantum phenomena because the nucleons which escape the nucleons have lower kinetic energy than the potential energy. Well, that's quite complicated. Quantum physics is all about quantization, the wave function, the Schrödinger equation, and so on. Okay, now let me tell you. We have to break just now, but you see, at the end of the 19th century, 19e siècle, at the end of it, people had done most of the things in classical physics. And classical physics includes classical mechanics, much more than we have done, but it includes the wonderful work of Maxwell's equation in electromagnetism, and it included thermodynamics, and all these things, they were done. And when Planck, as a young man at that stage, at the end of the 19th century, came to university, he was advised not to study physics, because basically everything is known in physics. This is what the people at that stage say. They said there were some small problems still, but it's not really something you should go for. You should study something else, not physics. And as you all know, Planck's name is on this board very often. He went and he studied physics. And the 20th century has been dominated by work that started with him and others, which is quantum physics. The whole 20th century, and plus relativity. We're not going to talk about relativity, but we're talking about quantum physics. And the quantum physics is such a huge change of thinking from what was the thinking of physics in the previous century. It's a tremendous change, and people have struggled to understand it, and there are many books on it. And people have really struggled to understand it. And I think most people feel reasonably happy with it now, although even in 1980 and so on, there were many experiments done to ask very specific questions about quantum mechanics, and they were answered in a specific way. They were answered in such a way that quantum mechanics, as formulated already in the 1920s and so on, was valid. So we have already here this idea that there is a wave and a particle. In a sense, you can think of water waves, and that is how people started thinking about waves. You have water waves, and you can say, but water waves are made up of many, many drops. And so it is a wave and a particle and so on. But that's not the right comparison. It is actually a single particle, a single drop, which takes this property of being both, can be considered as a wave and a particle. And this is something we should be thinking about. I'm just wondering about the time. Maybe I can just show this picture. So what do I do? Just on. Is it on there? Okay. One of the nice experiments to talk about quantum mechanics and thinking about quantum mechanics is the double slit experiment. Who knows what that is? The double slit. I'll start with that next time. Now, this is something which I took out of a book, and I just copied it, and maybe my copy is not right, but I think the story is still correct. If you have only, you're trying to take this photo, which actually in the book as it appears is a beautiful photo. It's my copy is not very well done. But the thing is, if you only do it with very little light, then you get just a few points. It's the same photo. Huh? Then you take more photons. These are the particles of light. Then you get something like that. And then you put in more like that, then you get that. And if you still take more, this, and then, so the number of photons are given here. So it shows you that you're taking this picture, but it is being created with a number of photons, and they are at random almost initially, as it appears. And if you get more of them, then you start getting the picture, and this picture is building up. So the language which I want to put to it is that with 3,000 photons, the probability of getting a photon here is still in a specific point is still very small. So I just get some of the photons, depending on chance. And then with more photons, I get more of these photons and so on. And now my question is to you. If I show you this sequence and I ask you to redo it with your camera, will you get the same sequence? Would you be able to reproduce this? I mean, experiments, we do experimental work by doing something, and then we want to be able to reproduce it. If you do a measurement, people want to check your measurement. If someone wants to check this and he wants to redo this, can he do it? Why not? I'm sorry this picture comes out so badly. I actually did it quickly this morning, and it's not this nice picture, but I can show you in the book. It's much more striking. But I think this to me is a striking example of what quantum physics is. It says these photons, they are all on the way to build this picture, but they come one by one. And if I only measure the first few of them, then I get just one getting here and one getting there and so on. And if I take a little more, then they are organized in the picture and so on. And if I redo this, they still come one by one, but in a different pattern. It is the same as if you take a die and you throw it, and eventually you get a certain distribution of ones and twos and threes and fours and fives and sixes. But if you get that distribution and you've finished it, and you say, well, I want you to reproduce this sequence which I have now just produced. Can you do it? No. And so the thing is that inherently, the things that happen in taking a photo with a normal camera, as most of you have such cameras, if you take in a little enough light, that photo will not give the image. It will just give you spots here and there. And if you make it the exposure a little longer, then it will give you more spots. But if you make it very long, then you will get this photo, and I will get this photo, and we'll all get this photo. Okay? But we will not get the same intermediate photos, the way it is being built up, because it is a statistical process.
What is the difference between the photon and the pixel?
This is why you can do these things so nicely these days. A photon is something which is light itself, and it hits a pixel and it changes the color of that pixel. It interacts with one pixel. And that is what's happening here. It interacts with one pixel. And so that pixel tells us, "Hi boys, there's a photon that hit me," you know? Okay? And but most of them are not hit. But now the next one comes, and the next guy says, "Oh, I'm also hit," and so on, you know. And so they show. So you can take with the camera, you can take these pixels that have been hit by a photon, and you can display it. And you don't even need to interrupt your experiment. You can keep on doing the same experiment. And it displays these pixels. And then as you go on, this picture is being built up. But it is being built up in a way which is different. Your picture is being built up differently than the one I'm taking. And each of us is taking the same picture, but it's being built up in different ways. And eventually, we get the same picture. So somehow, if we want to think that way, I don't, but if you want to think that way, you can think the photons know they have to go there because nobody was there yet, you know. So it's just a statistic, and if you have enough. So what happens actually is that the average number of pixels hit in this space is high, and here it's low, and that's why this is white and this is black. But when I still have very few photons coming in, then the pixels, well, only few of them are hit. And so even in this area, which eventually must be white, it is possible that no photon has hit there. I'll discuss the double slit experiment just now, tomorrow, and then we can come from this. And then we go away from this sort of thing. But I just want to tell you, quantum mechanics is a huge shift of thinking from classical mechanics. The basic thinking is very different.